So what we're going to start talking about now is statistics kind of things, probability kinds of things, expected value, variance, standard deviation. So let's start there. So intro to expected value, which is just another way of saying average or mean. Standard deviation and variance. Variance and standard deviation. Fix my screen here. Welcome, Natalie. Hit my video here. Let me go ahead and toss the attendance form in the chat while I'm thinking about it. There you go. All right, so let's say we've got some test scores. Let's say I gave a test in this class and only people take it. Let's say the scores of our test were 0, 0, 100, 100, 80, and 20. I obviously didn't write a very good test of those with the score. That's the point. So to find the average, we could write it either, and there's so much notation. And if you ever take a stats class, you'll see all these things. But some ways of writing the average are x bar or mu or e of x. Those are all things that mean the same thing. This is so just from a stats kind of terminology perspective, x bar is the sample mean, whereas mu is the population mean, meaning if you took a sample of the class, that'd be the average. But then if you took this like the entire population of UC Davis, that'd be mu. And then E of x is how we write expected value of x. But they're all calculated the same way, which is just you add up all the things and then divide by the number of things, which is 6. If we do that, we get 50. I will point out another alternative way of thinking about this is instead of adding up all the things and then dividing by the number of things, you take each thing, each score, and you multiply it by its frequency or its probability. So you could say, I'm going to have 0 times, well, there's 2 zeros, so 2 6 plus 100 times 2 6 plus 80 times 1 6 plus 20 times 1 6. You can kind of see that it's literally the exact same calculation, right? I have 0 plus 0 over 6 is 0 times 2 6. 100 plus 100 is 100 times 2 6. Sorry, 100 plus 100 divided by 6 is 100 times 2 6. What's it? Say that one more time? Oh, I did. Yeah, thank you. 1 6, not 1/20th. And this would also equal 50. The same calculation. Let me change some view here. There we go. It's better. How to make that go away? Oh, I guess I can't. So the way we think about calculating the expected value often is that the expected value of x is equal to each x value that occurs multiplied by its probability. So x1 times the probability of x1 plus x2 times the probability of x2, and so on and so on and so on. All the way to some last xn times the probability of xn. That's how we calculate. That's one way of calculating average or expected value. Variance on the other hand. So average is a measure of the middle. There are other measures of the middle as well. Whereas variance is a measure of how much difference from the middle there is, or how much literal variation there is in our scores. So to calculate variance, which we typically write as var of x or v of x. So you're going to take the difference between each score and the mean, and then square it, and then multiply it by its probability. So here it's going to be, well, my first score is 0. My average is 50. I'm going to square that and then multiply it by its probability of occurring, which is again 2 6. Same deal for the rest of them. I'm going to have 100 minus 50 squared times 2/6 plus 80 minus 50 squared times 1/6 plus 20 minus 50 squared times 1/6. By the way, and the reason we're squaring this is because if we didn't square it, we just did it like the differences and then multiply the probabilities, you would get 0 because these negative differences would cancel out with these positive differences. So that's why we end up squaring it. The reason we square instead of using an absolute value is because absolute value is cumbersome. It's just not a nice function to use. So a nicer way to guarantee that something's going to be positive without having to use the absolute value function is by squaring it. So we calculate this, we get, what? 2,500 times 2/6 plus 2,500 times 2/6 plus 900 times 1/6 plus 900 times 1/6, which ends up being 5,000, 10,000 plus 900, 11,800 divided by 6, which is, good question. Which is about 1,967. It's actually 1,966.6 forever, but we don't have to be super precise here. Once you know the variance, the standard deviation is just the square root of that. So the standard deviation which we often write as sigma, lowercase sigma, is just the square root of the variance. So in this case, standard deviation is the square root of 11,800 over 6, which is approximately 44.3. Standard deviation is a nicer way of talking about how much variability there is because it has the same units that you were originally measuring in. So for example, even though there aren't really units here, like the units are like points on your test, the variance is saying there's a lot of variance here. There's 1,966 points squared of variance, which is a weird thing to say. So in other words, what we're going to say instead is there are 44.3 points of variance when you talk about standard deviation. So that's a lot of variance, right? If the average is 15, we're saying your standard deviation is 44.3. That means there's a lot of deviation from the middle. I should say one more thing here. Two more. We keep saying things. The next thing I should say is that the way we calculate variance, so just like we had a formula for expected value, the variance formula is each score minus the mean squared times the probability of that score, or the frequency of that score. Really, frequency divided by the total. And then the next score minus the mean squared times the probability of that. And you just do that for as many different scores as you have. And just as a kind of counter or different example, if instead all 6 students got 50, so we scored 50, 50, 50, 50, 50, 50. What's the average? Right. What's the variance or the standard deviation? Right. There's literally 0 deviation from the mean for all the scores. So your standard deviation here would just be 0. Which doesn't usually happen, but so those are kind of the things we're going to be dealing with. Expected value, variance, and standard deviation. I'm curious about something. I don't actually know. So just on the off chance that he does it this way, I will point out that this expected value formula back here, he might write using the uppercase sigma notation. He might write this as the sum from I equals 1 to n of x sub I times p of x sub I. That's just a shorthand notation. For instead of writing all of this, I can write that instead. It just means you're adding up x sub 1 times p of x sub 1 plus x sub 2 times p of x sub 2 until you get to the mth x sub n times p of x sub n. And similarly, we could write the variance formula as the sum from I equals 1 to n of each x sub I minus the mean mu squared times the probability of x sub I. We don't have to write things that way, but sometimes it's convenient to do so. And he probably will talk about it. So it seems like it'd be silly not to talk about it right now. All right, let's look at some discrete probability. So we're gonna talk about discrete and continuous. When you think of things that are discrete, you should think of things where kind of you only have a finite number of typically integer options. So for example, some examples of things that are discrete would be like the number of people in a room. You can't have a fraction of a person. Or the shoe sizes people wear. You could have, but there'd be half sizes, right? So you could have like a 3 really small, like a 4, 4.5, 5, 5.5, 6, et cetera, et cetera, et cetera. Whereas as a counterexample, the length of someone's foot would be something that we consider continuous because there is an infinite number of possible values that you can have for the length of someone's foot if you measure finely enough. And it's what's kind of interesting is you can take something continuous like that and make it discrete by deciding how fine you want to measure. So for example, if I said, well, we're going to measure foot lengths to the nearest centimeter, well, then that becomes discrete because the only options are then, like 20 centimeters, 21 centimeters, 22 centimeters, et cetera, et cetera, et cetera. So there's kind of a fine line between discrete and continuous. Time is also considered to be a continuous variable. We often talk about like the amount of time we wait for a bus to come. That's usually an example for some reason. And your time can be anything from like 0 to 20 minutes. And then that's going to be continuous because there's an infinite number of possible times you could wait. And again, if we wanted to, we could make that discrete by saying, well, we're going to measure time to the nearest minute. And then there's only like 20 options. So that's kind of the general difference between discrete and continuous. Let's start by talking about some discrete probability, which is in section 9.1. Discrete probability. And actually, before I say anything else, I should also say that when you're trying to find the probability of a thing happening at a very kind of basic level, you're asking to calculate the number of times something happens divided by the total number of ways anything can happen. Is very generally how you calculate the probability of something occurring. Yeah. So let's look at this example. A coin is tossed 4 times. We're going to let X equal the number of heads that come up. So first, we're going to list the sample space. And the sample space is just the set of all possible outcomes. So if I flip 4 coins or 1 coin 4 times, I kind of actually like to imagine this more as flipping 4 coins that I've painted different colors, like red, blue, orange, and green. So that like when I get, for example, if I have like a red, blue, orange, and green, well, it looks different if I have heads, 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 tails versus heads, heads, tails, heads. Right? It looks different that the green coin is showing up as tails versus the orange coin is showing up as tails. Even though both of these outcomes end up with 3 heads and 1 tails. They are considered different, and so we have to count them each separately. So to list the sample space, it's good to be systematic. Let's start off by saying, well, what does it look like if we have 4 heads? We all have 4 heads, but that's not a great joke, but it's the only one I got. So if we have 4 heads, that looks like all the coins are heads. And nothing else can happen, right? There's only one way of getting all 4 heads. You get all 4 heads. What about getting 3 heads? Well, then there's going to be a few ways of getting this. We can either have, and so here's what I mean about being systematic. I'm going to start by writing heads, 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 tails. And I'm just going to kind of imagine that tails moving 1 over each time. So I'm going to have heads, heads, tails, heads, heads, tails, heads, heads, tails, heads, heads, heads. or we could have 2 heads. This is the one that's the most challenging to be systematic about. So I'm going to start off with all my heads to the left, all my tails to the right. And then I'm going to let this kind of leftmost tail scooch over to the left. So I'm going to say, okay, I'm going to have heads, tails, heads, tails. And then I'm going to have tails, heads, heads, tails. Now that that tails has scooched as far over to the left as possible, I'm going to scooch it back, but I'm going to move, well, first I'm going to move this other tail's left one, and then move the other tails back. So I'm going to have heads, tails, tails, heads. And then I repeat the process. I'm going to scooch this one over, tails, heads, tails, heads. That's as far over as it can go. So then I scooch the other one over, and I get tails, tails, heads, heads. I'm pretty sure those are all the different ways I can have 2 heads and 2 tails. It's a little bit complicated though. It'd be harder if there was more things. Fortunately, we're gonna have a way of dealing with this. If I want just 1 head, well, that's the same as having just 1 tail. I'm just interchanging the heads and tails from x equals 3 over here. So I'm gonna have tails, 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 heads, tails, tails, heads, tails, tails, heads, tails, tails, or heads, tails, tails, tails. And finally, if I want 0 heads, that's all tails. And those are all the ways or all the possible outcomes that can happen when I flip 4 coins. So how many total are there? Well, there's 1 way here, plus 4 ways here, plus 6 ways here, plus 4 ways here, plus 1 way over here, which is a total of 16 possible outcomes. It's also worth noting here that we could have calculated how many possible total outcomes there were by observing that each coin has 2 possible outcomes, heads or tails. So if you multiply 2 times 2 times 2 times 2, you're going to get 16. Another way I like to think about this is you could literally make a branching tree of all possible 16 outcomes. You don't really need to do this, but I'm going to do it one time just to kind of show it. So at the first flip, I have heads or tails. And then for each of those, I have heads or tails. I never give myself enough room on this tree. Let me be smart about this. Let me make it, no, it's fine. I'll make it work. I think this pen's running out of ink. And then each of those have heads or tails. Trying to make it fit. And then each of those have heads or tails. I know is not the prettiest work I've ever done. Sorry. But literally, by following any one path here, you can see all 16 of these possibilities show up. Heads, 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 heads. Heads, 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 tails. Heads, heads, tails, heads. Heads, heads, tails, tails. Heads, heads. I've done with heads, heads, right? Yeah. Heads, tails, heads, right? You can just keep going and you get all 16 of those possibilities. And each one of them is different because each one of them has to take a different branch of the path. But there are literally 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 16 different possible ends of the path we can get to. And each pathway is unique. So yeah, 16 possibilities. Let's make a table. What's the word I'm looking for? A probability table. Sounds fancier than it is. I'm really just going to write all the values and all the associated probabilities. So I have X and the probability of X. So the values X could be, and again, X was the number of heads. X could be 0, 1, 2, 3, or 4. And the probability of X is just the number of ways of getting the thing you want divided by the total number of ways anything could happen. So the probability of getting 0 heads is, well, there's 1 way of getting 0 heads out of total 16 total things that can happen. The probability of getting 1 head is 4 out of 16. Probably getting 2 heads is 6 out of 16. Probably getting 3 heads is 4 out of 16. And probably getting 4 heads is 1 out of 16. And notably or importantly, these probabilities add up to 1 plus 4 plus 6 plus 4 plus 1 is 16 out of 16. The probabilities of something happening should always add up to 1 or 100%. Because if you've covered all the possibilities, then any of those things happening should happen with a probability of 100%. So then we can use this fact to calculate stuff. Like, for example, what if I wanted to find the probability of getting at least one head? Right, so I want the number of heads to be 1 or greater. Well, one way I could do that would be just to add up all the things. I could say that's going to be the probability that x equals 1, plus the probability that x equals 2, plus the probability that x equals 3, plus the probability that x equals 4. And I can add those all up and get 4 over 16, plus 6 over 16, plus 4 over 16, plus 1 over 16, which is going to be 15 over 16. Which is fine in this problem, like it's not too much work, but if I was flipping 40 coins instead of 4 and wanted to add up all those things, it would be really, really tedious. And I don't have to. But I could instead say, well, I know that this probability, if I just added on that last one that I'm missing, would add up to 1. So instead of saying probably x greater than or equal to 1 is this, I could say, I know the probability that of x being less than 1 plus the probability that x is greater than or equal to 1 has to equal everything. That's all the possibilities, right? Either x is less than 1 or x is bigger than or equal to 1. There's no other choice. But that means if I want to find this, I could say, well, the probability that x is bigger than or equal to 1 is equal to 1 minus the probability that x is less than 1. But if x is less than 1, there's only one thing x can be. What is that? So if x has to be smaller than 1, and these are the options for x, what's the only number that's actually smaller than 1 up there? Right, the 0. So that's really the same as saying 1 minus the probability that x is equal to 0. The probability that x is equal to 0 is 1/16. So we're going to get 1 minus 1/16, which is exactly 15/16. And that's usually the way you would actually want to do a problem like this. And this is called the complement. Or as I like to think of it, the leftovers. Right? Instead of adding up all the things you want, add up all the leftovers and subtract them from 1, and you'll get the probability of what you want. Pen. Yeah, you're good. Okay, so we can also ask, what's the expected value? What is the expected value for the number of heads? Or in other words, what is E of x? Well, there's a short way and a long way of doing this. In some of these problems, your intuition might be more helpful than others. Here, if I said, I'm going to flip 4 coins, how many of them would you imagine would probably come up as heads? 2 of them, half of them, right? And that's exactly the right answer here. Even if we do it the long way, the expected value of x is going to be, well, the first x value times the probability of that, plus the second x value times the probability of that, and so on and so on. Which is really just going to be 0 times 1/16 plus 1 times 4/16 plus 2 times 6/16 plus 3 times 4/16 plus 4 times 1/16, which ends up being 0 plus 4 over 16 plus 12 over 16 plus 12 over 16 plus 4 over 16, which is 32 over 16, which is 2. Now is that really important? I'm sorry, I'm teaching another class right now where we're doing more of the stat stuff. So I'm like, oh, we could talk about this, but there is like a nice formula for this, which is just the number of coins you're flipping times the probability of getting a head, which is 1/2. But that's not really where we're going with this class, so I feel like we can just leave that off. How about the variance? Okay, so the variance is almost always kind of gross to calculate by hand, but it's not terrible. So the variance here is going to be each value minus the mean squared times probability. So it's going to be, let's write it down here, 0 minus 2 squared times the probability of 0, which is 1/16, plus 1 minus 2 squared times the probability of 1, which is 4/16, plus 2 minus 2 squared times the probability of a 2, which is 6/16. But we know that's going to be 0 because 2 minus 2 is 0. Plus 3 minus 2 squared times 4/16, plus 4 minus 2 squared times 1/16. So calculating this out, we're going to get 4 times 1/16, which is 4/16, plus 1 times 4/16, which is 4/16, plus 0, plus 1 times 4/16, plus 4 times 1/16, which is 4/16. So I end up with 4/16 plus 4/16 plus 4/16 plus 4/16, which is equal to 1. So here the variance is 1, and the standard deviation, which is the square root of the variance, is also 1. So for probability stuff, like for discrete probability like this, the idea is usually that we would like to be able to have, I think really the most useful thing here is this probability table is allowing us to make all these calculations. Let's look at another example, something a little bit different. So let's suppose we have a game. Suppose this table could be a little bit higher. How about that? Try not to bend over too much. Is that too high though? That might be too high. A little too high. Sorry. Okay. Suppose a game is made in which player receives $5 for flipping 3 heads or 3 tails out of 3 coins, right? We're not flipping 4 coins, but loses $2 for anything else. I don't love the following question. So the way this is phrased is this game fair? And a fair game would mean, on average, you'd expect to win $0. I think a better question is, should I play this game? Would I expect to win more than I'm going to lose? Well, I don't know. Let's find out. I really actually don't know the answer. So let's see here. So here's how I would calculate this. So there's 2 possible outcomes for the amount of money I win. So I could either, if I'm making my probability table, my X value and my P of X values are, well, X could either be, I could win $5, or I could lose $2, which means I'm going to win -$2. So typically, if you're getting money, we think of it as getting positive. If you're losing money, you're getting negative money. Now, let's write out the possibilities. So if I'm flipping 3 heads, well, actually, let's be smart about this. If I'm flipping 3 coins, how many possibilities should there be? 3 coins. The total number of possibilities is how many? Possibilities, sure. Do you have a guess, Cassie? Right. 2 times 2 times 2. How many ways can I get 3 heads? Only 1. Right? For all 3 coins to be the same, there's only 1 way that can happen. How many ways can I get 3 tails? Right. So the number of ways I can win $5 is 2 out of 8. Which means the number of ways I can lose $2 is how many? Right. Now, if it wasn't quite so easy to see what we had here, we would make the list of the sample space. And the sample space would be tails, 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 and then we'd have tails, tails, heads, or tails, heads, tails, or heads, tails, tails for one head, and then tails, heads, 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 tails, heads, 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 tails for one tail, and then heads, heads, heads over here. And then we can see, oh yeah, these 2 ways are the ways we win, these 6 ways are the ways we lose. Great, so what's the expected value of x? Well, it's going to be the value of x times the probability of x plus the value of x times the probability of x. So that's going to equal 10 divided by 8 minus 12 divided by 8, which is going to be negative 2 divided by 8, or negative 0.25. Which means the expected value of this is negative 25 cents. Now, just to be clear, the expected value is an actual number you usually get. Like, for example, if I was going to flip these 3 coins, the expected number of heads would be 1.5 heads. You don't ever actually get 1.5 heads, but over the course of many, many, many flips, you would expect the average number of heads to tend towards 1.5. Just like with here, if you keep playing this game for a long, long time, you're going to expect to lose an average of 25 cents every time you play. So if you played this game 100 times, you would expect to lose 100 times 25 cents, which would be what, 40 bucks? I think. Is that right? No. 25, 40 bucks, James. 1, 2, yeah, $25. I don't know. Yeah, I know where I come out of it. So every time we play this, right, you might win $5 here, lose a couple dollars, lose $2 a couple times, win, lose, but eventually, if you do this long enough, you're going to expect to lose an average of 25 cents every game. So if you played 100 times, you expect to lose $25. So we shouldn't play. If you're asking the question, is the game fair? The game is not fair. The only time a game is fair is if the expected value is 0. On average, you expect to win $0. So sometimes you win, sometimes you lose. Yeah. How much time we got? Well, we got so much time. We're going to get through both these sections here. Let's do this next example. I should look at, I have other examples too. Let me grab this other sheet of paper here. Where did you go? Sorry, 1 second. There you are. We'll do a bunch of these examples. These discrete ones are good. So let's look at this example. Insurance claims and their probability are shown in the table below. What should the annual premium be so that the insurance company breaks even? Really, what the question should really be, how much did they charge so that they make a profit of X number of dollars per person, right? Because most insurance companies are not nonprofits. They're there to make money and also provide a service. So here's our table. So X, which is the amount of a claim, and P of X, which is going to be the probability of that amount. So X equals the amount of the insurance claim. Just because my wife works in insurance, so I could speak to this a little bit. Obviously, you don't get claims that are all exactly the same dollar amount. So we're just kind of averaging things out here. So on average, 93.6% of people make a claim that is worth $0. Or in other words, 93.6% of our insured members don't make a claim that year. And then we have 0.040, so 4% of insured people make a claim that averages value of $1,000. This question would be better if they had a deductible in there. $5,000 claims, 2% of our claimants are making. And finally, $10,000 claims, 0.004 or 0.4% of our insureds are making. The question, although there's a lot of words, they're really just asking you, what's the expected value of an insurance claim? On average, how much do we expect each insured to make a claim for? Well, let's find out. The expected value of X, just like before, it's each value multiplied by the probability of that value. So it's going to be 0 times 0.936, which is just 0. I feel like silly even writing that, but good to write it. And then $1,000 times 0.040 plus $5,000 times 0.020 plus $10,000 times 0.004. Which ends up equaling $0 plus $40 plus $100 plus $40, which is $180. So we expect each member on average to make a claim of $180 in a year. And so that's what we're going to charge each person. So we should charge each member $180. Most people won't use it, right? That's the whole point of insurance. You don't want to have to use it, but you have to buy it. So all of these people here, yeah, they're going to lose out $180 that year. But maybe next year they have an accident. Whereas right, all these people over here, they're going to win by getting in an accident. I mean, you're not really winning, but right, you're getting value. But you don't want to get that value really. Let's grab this sheet over here. So we got so much time. Let's look at a couple more of these. Yeah, let's look at that. A couple more expected value questions, and then we'll move on to the continuous stuff. I don't love that one. Let's do this one. Okay. A bag contains 20 golf balls, 10 of which are white, 7 of which are red, and 3 of which are blue. We're playing a game again, by the way. So you pay $3 to select one ball. If you pick the white one, you win $1. If you pick the red one, you win $4. If you pick the blue one, a blue one, I should say, you win $10. I think the best way to ask the question is, should we play this game? I suppose I could give more context. If we're interested in winning money, not losing it, should we play this game? Which usually is, well, what's the expected value? So let's let X equal the net amount of our winnings. So there's going to be 3 potential amounts here. So if we pick a white ball, how much money did we win? Well, yes, we did. Let me ask, so how much money did we pay? So what's our net winnings? Well, I would say, no, you're right with 2, but I would say -2, because we've actually lost money, right? We're out $2. So we're going to lose $2 10 out of 20 times. Because there's 10 white balls out of 20 total. What if we pick a red ball? Well, then we won $4, but we paid $3, so we're going to win a net of +$1. And that's going to happen 7 out of 10 times. And if we pick one of the blue balls, we're going to win $10, but we paid $3, so our net winnings are going to be $7, 3 out of 10 times. So then the expected value of X is going to be -2 times 10 out of 20 plus +1 times 7 out of 20 plus +7 times 3 out of 20, which ends up being -20 out of 20 plus 7 out of 20 plus 21 out of 20, which ends up equaling what? 8 out of 20? Which is, I'm gonna write that as 4 out of 10 or $0.40 or 40 cents. So on average, we can expect to win 40 cents each time we play. So we should play this game. So if we played this game 10 times, we would expect to win on average $4. If we played this game 100 times, we would expect to win on average $40. The thing about games like this is you do have to play, like to actually have the averages eventually work out to account for the variability. You have to play a long time to make sure that you don't have too much variance and lose before you can come back up. So yeah. All right, let's talk about continuous probability. For things that are not discrete, but continuous. So section 9.2, continuous probability. So let's look at this example. The weight of a potato in pounds is modeled by the probability density function. Which we often abbreviate as PDF. F of x is equal to 3 divided by 14 times the square root of x, and x is between 1 and 4. So what we're saying is the weight of the potato can be any weight between 1 and 4. And the likelihood of getting the specific weight, well, that's where things get a little bit weird, because the probability that the potato weighs, like, say, exactly 2 pounds, and it's gonna sound weird, the probability that the potato weighs exactly 2 pounds is essentially 0. It's tending towards 0 because there's a very, 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 very minuscule window of getting that exact weight. Like, it's almost impossible to get a potato that weighs exactly 2 pounds if you weigh it finely, right? If your scale has decimals upon decimals upon decimals, eventually you're going to get to a point where you're deviating from 2 pounds exactly. So typically any one value, probability of that any one value for something that's continuous tends towards 0. So we don't ask questions like that. So let me actually draw this picture here before I get to. So this function, 3 over 14 root x, well, if x is 1, the square root of 1 is 1, and 3 over 14 times 1 is 3 over 14. So 1, 2, 3, 4. And when x is 1, the value is like 3 over 14. And when x is 4, square root of 4 is 2. 2 times 6, 3 is 6, like 6 over 14. So I can make this look a little bit nicer or whatever. So it's going to look something like this. So there's my function showing the probabilities for each weight of a potato. And so what I want to ask, actually what I want to point out first is that the area under this curve has to be equal to 1. Because the total amount of probability should add up to 1. So that area is equal to 1. We could check it, although if they've told you something is a PDF with a specific interval, we can always make the assumption that that should be true because it has to be true. So either they've either made it true or they made a mistake. So here's the first question I want to ask. What is the probability of a potato weighing between 1 and 2¼ pounds. Well, that question really is, how much area is under the curve between x equal to 1 and x equal to 2.25? So really, we're asking, let's make it a little bit more exaggerated. We're really asking here is to, let's say right there, find this area. Find the area under the curve for x between 1 and 2.25. Well, great. We definitely know how to find the area under a curve. We've been doing this for a little bit now. That's going to be the probability that x is between 1 and 2.25. Oh, let's change 2.25 to a fraction. That's 2¼ which is 2⁴, which is 9/4. And here's what this is going to equal. It's going to be the integral from x equals 1 to x equals 9/4 of that function, of that PDF, which in this case is the function 3/14 times the square root of x, or times x to the 1/2 if we want to make it less terrible. And that's typical for any sort of probability question for a continuous random variable. When we say, what's the probability that your variable is between two numbers, you're just going to do the integral of your PDF from the lower number to the upper number. Here, let's see what that ends up being. So we're going to get 3/14 times the integral of x to the 1/2 is x to the 3/2 times 2/3 from 1 to 9/4. So simplifying a bit, 3/14 times 2/3 is 2/14, which is 1/7. And then we're going to plug in. We're going to get 9/4 to the 3/2 minus 1/7 times 1 to the 3/2. I probably would have just factored out the 1/7 if I was thinking about this in advance. That's going to be 1/7 times, okay, 9/4 to the 3/2. I would point out that both 9 and 4 are square numbers. 9 to the 3/2 is going to be 9 to the 1/2, which is 3, and then that number cubed, which is 3 cubed, which is 27. 4 to the 3/2 is the square root of 4 to the 3rd power, which is 2 cubed, which is 8. More easily, 1 to the 3/2 is just 1. So we end up with 1/7 times 27 minus 8 is 19/8, right? Because 27 minus 8/8 is 19/8. So we get 19/56. I don't particularly care that the value is that number. The only thing I really care about making sure is true is whatever that probability is, it should be positive, or I should really say non-negative. I guess the probability could be 0, and it should be less than or equal to 1. Your probability should always be between 0 and 1. You can't have more than 100% probability of something happening. You can't have less than 0% probability of something happening. Okay. Follow up, or second part. What's the probability that the potato weighs more than 2.25 pounds? But I should also clarify, since we said the potatoes had to weigh between 1 and 4, I should say more than 2.25 pounds, but still less than 4. Or less than or equal to 4. Well, the hard way to do this, or the more work way to do this, would be to say, well, I'm going to do the integral from 2.25 or 9/4 to 4 of the same function. But I don't have to do this work. And the reason why is because I know that if this area up there is 956, sorry, 1956, that this area over here, the leftovers, should be 1 minus what I just calculated. So this should equal 1 minus the previous integral, which is just going to be 3756. And that is what you would get. So we use this complement idea quite a bit. If you're being asked to calculate something and you've already calculated the other remainder of it, or I should really say the complement of it, don't calculate this the long way. Do 1 minus that. It's really useful when we start getting into ones that are improper. So that instead of calculating like the integral of something to infinity, you say, well, instead of calculating that, I'm going to do 1 minus the other part of it, which is finite, which is nice. Let's look at some more. Yes. So here's where things get interesting. So what's the expected value of the weight of the potato? Well, for discrete random variables that we were just talking about before, the expected value of x was each x value multiplied by the probability. So x1 times p of x1 plus x2 times p of x2 plus all the way to some xn plus p of xn, which you could certainly write as the sum from I equals 1 to n of x sub I times p of xi. That's the discrete version of the expected value. The analogous continuous version. So when we go from discrete to continuous, we go from a sigma notation to an integral notation. So the expected value for a continuous variable is going to be, instead of each x sub I times the probability, and then we're adding them up, we are quote unquote adding them up. All of the x's times their probability, f of x. Some people use a p of x there, but I think the book uses f of x, so we should use the book. From your lowest x value to your highest x value, which in this case are 1 and 4. But more generally, right, if your PDF is some function from a to b, and the area under that curve has to be 1, then the expected value of x here would be the integral from a to b of x times f of x. But it is worth noting, and I should say this here, that it is also true that if this is a PDF, right, if this is f of x is a PDF, then the integral from a to b of just f of x on its own has to be equal to 1. Just like for discrete things, all the probabilities have to add up to 1. So great, that's fine, but now calculating this is really kind of gnarly a lot of the time. So for this problem, the expected value of x is going to equal the integral from 1 to 4 of x times r 3/14 times x to the 1/2. And things are probably going to get kind of gross here. Let's pull out the 3/14 in front, and x times x to the 1/2 is x to the 3/2. And now we're going to integrate that. So we're going to get 3/14 times x to the 5/2 times 2/5 from 1 to 4. 3/14 times 2/5, I can cancel a 2 there and a 2 there. So I really have 3/7 times 1/5, which is going to be 3/35 times 4 to the 5/2 minus 1 to the 5/2. Before we get our answer here, looking back at our original function for these potatoes that weigh between 1 and 4 pounds, we would expect our expected value to be between what numbers? Right. We shouldn't be getting an expected value that's outside of the interval that the variable lives on in the first place. Probably somewhere nearish the middle, right? But definitely, if you get an answer that's like 5, that's a problem. right? We know we shouldn't be getting something larger than 4 or smaller than 1. So here, yeah, 4 to the 5 halves, so we get 3/35. 4 to the 5 halves power is 2 to the 5th power, which is 32. And 1 to any power is 1. So you end up with 32 minus 1, which is 31. 31 times 3 is 93/35. Which is a little bit less than 3. Right? Because 93 is not quite 3 times as big as 35. If you really wanted to, you could write this as a mixed fraction, although we usually don't. You could say it's 2 and 23/35 of a pound. Okay, so like 2 2/3 of a pound, approximately. That's the expected value here. So on average, an average potato is going to weigh that much. That doesn't mean any one potato is actually weighing that much. It just means what you get. Let's talk about the variance for a second. So just like the variance, so for the variance, the discrete version was the sum from I equals 1 to n of each x value minus the mean squared times the probability of that x value. So the continuous version, well, we'll say the not very nice continuous version is just the same idea, except you're using integrals instead of sums and your function f instead of your function p. So it's going to be the integral from, I'm going to write it very generally first here, from a to b of x minus the mean squared times f of x dx. So here's what this would look like in this problem, which we're not going to actually do, but I'm going to show you first. So for our problem here, the variance of x is going to look like the integral from 1 to 4 of x minus the mean, which was, oh, sorry, sorry, it's chat. I keep missing the chat. Sorry, apologies for missing the chat. Sorry. You guys, again, if I miss the chat, you really very welcome to unmute yourself and say words. You might scare the crap out of me, but that's okay. But it looks like you got it. Yeah, the answer was 2 and 23/35. I would have probably left it as 90, what is it, 93/35. But yeah, sorry about that. Don't hesitate to say words if you need to say words. So here, the terrible way of calculating the variance would be x minus 93/35. Oh, sorry, there's more chat. I should just keep the chat up. Why don't I keep the chat up? Yeah, cool. All right. So x minus 93/35 squared times 3/14 times the square root of x. Wow, that looks terrible. So I'll tell you, there is an alternate formula for the variance, which we almost always use. And I would like to show you where it comes from because I think it's kind of neat. So let's actually look at this formula here, and we're going to work with this for a second. So here's the alternative formula. And you don't need to write this down necessarily, but you're certainly welcome to if you want to. So I'm going to take this integral. I'm not going to write the limits of integration because we know that they're just from a to b, or from whatever your lowest to your highest is. So the integral of x minus mu squared times f of x dx. I'm going to remind everybody that mu is a constant. It's whatever we found for the expected value. In this case, it would be 93/35. But in general, it's just whatever your expected value or your average is. So we're going to treat it like a constant. So let's multiply this out. I've got x squared minus 2 times mu times x plus mu squared. All of that times f of x. Cool? Okay. So then distribute the f of x. You're going to get the integral of x squared times f of x. And yeah, minus 2 times mu times x times f of x plus mu squared times f of x. Now we're going to break this apart into 3 integrals. We're going to write it as the integral of x squared times f of x dx. Okay, watch this next part here. For the next integral, I'm going to bring out the constant, which is minus 2 times mu. So write it as minus 2 times mu times the integral of x times f of x dx. Plus, I'm going to bring out the mu squared as well, because mu squared is a constant. times the integral of f of x dx. And now actually I'm going to add back in the a's and b's because I want them. I didn't really want to write them all each time, but I decided I wanted them. Okay, super important question, which is going to fall on Cassie to answer because she's the only one in the room. But I think she's going to get it. It's all right. What's the integral from the very bottom to the very top of just the function have to be equal to? Well, it's from 1 to 4, but we're in right. So if I look back at my picture here, sorry, let me grab my picture here. If I said, what's the integral of this function from 1 to 4, or in other words, how much area is under the curve? It's got to be 1. There's no other choice. So no matter what, if you're doing the integral from the lowest possible bound of a to the highest possible bound of b of your function, that's just equal to 1. Okay, I know I just wrote it on the previous page. What's another name for the integral from as low as a to as high as b of x times your function f of x? If we look back at the previous page, if I can get it, that's how we calculated the expected value. The expected value of x, or the mean, is just the integral from the lowest value of a to the highest value of b of x times f of x. So this here, this integral from a to b of x times f of x is just equal to the mean. So look what we've got. We've got the integral from a to b of x squared times f of x. There's nothing to do with that. That just is what it is. But then you've got minus 2 times mu plus mu squared times 1. Or the alternative formula is equal to the integral from a to b of x squared times f of x minus 2 mu squared plus mu squared is minus the mean squared. And that's much, much nicer. It's much less terrible to integrate x squared times f of x and then subtract off some constant than it is to do this gross thing that I wrote up here. So whenever you're calculating the variance, especially if it's for continuous random variables like this, you should almost always default to using the alternative formula here. There's no good reason I can think of to do it the harder way. So instead of doing that, we're going to say that our variance is equal to the integral from 1 to 4 of x squared times our function. And then after we do all that, we're then going to subtract off the mean squared, which is still gross, but it's not nearly as gross. Okay, so then let's do it. So we're going to get, let's see. So let's bring the 3/14ths out in front. And x squared times x to the 1/2. Well, 2 plus 1/2 is 5/2. So we have x to the 5/2 minus whatever this number over here is. And then integrating x to the 5/2, we get x to the 7/2 times 2/7. So we have 3/14 times 2/7 times x to the 7/2 from 1 to 4, still minus the same number. 3 times 2 is 6. 14 times 7 is 98. I feel like I could have canceled this. I could have been smarter about that and canceled the 2 here and the 2 here and really gotten 3/49, which I'll write in my next step. And then plugging in 4 and 1, I get 4 to the 7/2 minus 1 to the 7/2 minus this 93/35 squared. This ends up being 3/49. 4 to the 7/2, which is the same as 2 to the 7th. All right, 2 to the 7th, 2 times 2 times 2 times 2 times 2, that's 32, times 2 is 64, times 2 is 128. Minus 1, minus that. And I think we've simplified this enough, in my opinion, but I guess we can go one more step. That's 127 times 3 is 381. Really, I probably should have used the calculator a while ago and just said it's some number. It's approximately, I don't know, Let's find out. Let's use the calculator. Did I put my calculator away? That seems like a silly choice. No, put it that way. So let's see here. 93 divided by 35. I guess we're squaring that. That's terrible. About 7. And then 381 over 49 minus that. We're getting approximately 0.715. And then we take the square root of that to get the standard deviation. So this, which actually gets bigger, right? So your standard deviation is approximately the square root of 0.715, which is approximately 0.846. Okay. So potatoes, these potatoes have an average weight of about 2 1/3 pounds, and their standard deviation or variability is about not quite a whole pound, but close to a whole pound, 85% of a whole pound. Okay. That seems plausible. Cool. So sometimes people ask questions like this where they give you a probability density function and ask you to find like the expected value or the variance or a probability of the probability between two values. Other times, they give you not quite all the function and ask you to figure out what it needs to be a PDF. So let's look at this next example. Let's say that we have given that f of x is equal to k divided by x squared on the interval from 1 to 3. Find the value of k, or for k, so that f of x is a probability density function. Or in other words, do the integral of this function and set it equal to 1 and then solve for k. So we're going to set the integral from 1 to 3 of k divided by x squared equal to 1 and solve for k. So really, I would do the integral, and then after I'd finished doing the integral, then I would set it equal to 1 and solve for k. I suppose if you wanted to, you could also factor out the k since it is a constant and then divide both sides by the integral. So really, if you really wanted to, you could say that k is equal to 1 over the integral from 1 to 3 of 1 over x squared dx. But that feels kind of weird to me. So I would just work with this. So let's see, working with the left-hand side here, I am going to factor out the k. So I have the integral from 1 to 3 of x to the negative second. And that's going to equal k times, let's see, the integral of x to the negative second is x to the negative 1 divided by negative 1 from 1 to 3. I really don't love writing this way. I would really much rather write it as k times negative 1 over x from 1 to 3, which ends up being k times negative 1/3 minus negative 1/1, just negative 1. So that's negative 1/3 plus 1, which is 2/3. I'm getting k times 2/3, and I want that to equal 1, which means k is going to equal 1 divided by 2/3, which is 3 over 2. So k equals 3/2 is the value of that constant that makes this function a PDF on that interval. So cool. Now we can write that our function f of x equal to 3/2 over x squared, or I would probably actually write this as 3 over 2x squared is a PDF on the interval from 1 to 3. We do have to state the interval though, right? If you just say it's a PDF and you don't give an interval, it's meaningless because like, what's the interval? There are lots of different intervals that actually would work. We have to select one of them. So then we might ask the question, oh, what time? Oh, we got 9 minutes. We got plenty of time. We could ask the question like, what's the expected value? So what is the expected value of this f of x equal to 3 over 2x squared on the interval from 1 to 3? It's the same thing. So whenever you get asked the expected value for a continuous thing, you're just taking the integral of x times your function. So the expected value here, or if you prefer mu, is going to be the integral of x times our function, 3 over 2x squared. What should my limits of integration be? Right. For expected value or variance, it's always the full interval. So from your lowest value to your highest value. We're going to simplify. I'm going to write this as 3 over 2 brought out in front times the integral of x over x squared reduces to 1 over x. If we integrate that, we're going to get the natural log of the absolute value. Oh, don't forget the limit of integration. So we're going to get 3/2 times the natural log of the absolute value of x evaluated from 1 to 3. So that's going to be 3/2 times the natural log of 3. I don't need to write the absolute value of 3 because the absolute value of 3 is 3. Minus the natural log of the absolute value of 1 is 1. The absolute value of 1, or sorry, the natural log of 1 is also 0. So our answer ends up just being 3/2 times natural log of 3. Which I assume is some number between 1 and 3. Because it has to be. Oh, here's a good question. I forgot about this. I forgot about this stuff. So the expected value or the average is, how to say it the right way? It's a weighted average. So I wish I had a better example here. What I'll point out here is, like in the previous example we did with the potato. 1 second here. Maybe. Sorry, I can't find it anymore. Where'd you go? There you are. Like in this example here, right, we found the probability, or sorry, we found the expected value to be 93/35 of a pound, which is like 2 2/3 almost pounds. So that's kind of like maybe, I don't know, right there. What you should think of that being kind of physically is the place where the area would balance. Not that there's half of the area on the right and half the area on the left, but if this was like a seesaw, it would balance there. So that area that's further away from the middle kind of has more of an impact. Whereas area that's closer to the middle has less impact because that, right, if you're the smaller person on the seesaw, but you sit further out, that lever arm gives you more effect. It's kind of like the physics of it. So the average or the expected value is the kind of middle balancing point, whereas the median is the place where half of the values are below that number and half of the values are above that number. And median sometimes is a better measure of the middle. Especially when we talk about things like household income, we almost always refer to the median household income because there are not lots, but there are some people that make exorbitant amounts of money, and they would really skew the average to be much, much higher than what really would be a good measure of the middle. So the median is the value where half of the area is above that and half is below. Or in other words, the median is the value that separates the top half from the bottom half. How do we find the median? Well, to find the median, we're going to set the integral from 1 to whatever the median is. I don't know, so I'm going to just use m of my function equal to 1/2. Or if it makes more sense, you can set the integral from the median to the top value of 3 over 2x squared equal to 1/2. Either way is correct, but sometimes, again, I'm going to go back to the example we haven't done yet, where if you had like something that was improper and your integral was from like 1 to infinity, you definitely want to do the integral from 1 to m equal to 1/2, not the integral from m to infinity, because we'd always rather deal with the proper part if we can. So set these equal to 1/2 and then solve for m. So let's look at this one here. So I'm gonna take the integral of this, we already did, right? The integral of 3/2, oh no, we didn't, sorry, let's just do it over here. So this is gonna be integral from 1 to m of 3/2 times 1/x² dx. That's gonna be 3/2 times, the integral of 1/x² is, I'm not gonna write x to the -1 over -1. I'm just gonna write it as -1/x. I feel like we've integrated x to the -2 enough times that we know it's x to the -1 over -1, which is -1/x. From 1 to m. Plug in our values. We have 3/2 times -1/m minus -1/1. Or in other words, 3/2 times 1 minus 1/m. And we're going to set that equal to 1/2. And then we're going to solve for m. So I would probably take the first step of multiplying both sides by 2. So 3 times 1 minus 1/m is equal to 1. And then you could either distribute the 3 or divide both sides by 3. I'd probably choose to distribute. I feel like it's easier to do that than adding or subtracting fractions. I'm going to have 3 minus 3/m is equal to 1. I like to keep things positive. So I know most people probably like subtract 3 from both sides. I would much rather subtract 1 from both sides and add 3/m to both sides. So the 2 equals 3/m. I don't love that this is going to be what I think it's going to be. That's fine. Oh, no, that's fine. That's fine. Yeah. No, I was wrong. It's not going to be what I thought it was going to be. Cool. So that means we get 2 times m equal to 3, or m equal to 3 divided by 2. So the median here is 3 divided by 2, which is coincidentally the same as the k value we found in the beginning, but that has nothing to do with one or the other. Here's what this looks like graphically. So our function, f of x, is 3/2x² on the interval from 1 to 3. So graphically, we've got something that looks like this. When you plug in 1, you get 3/2. When you plug in 3, you get 3/2 times 9, which is 3/18, which is 1/6. So it definitely comes down sharply like this. That, and it continues on that one. What we're saying is the median is at 1.5 or 3/2. So right here, there's your median that separates the lower half of the data from the upper half of the data. Now my picture might not be great here because the way I've drawn it, it kind of looks like there's more area to the right than there is to the left. But really, so probably this should be a steeper decline here. But that's the idea, is that value does actually separate, right? There's half the area over here, half the area over here.